What we're going to look at then is the powers. So raise it to a power. That being a whole number, we'll worry about fractional powers or roots later. So n greater than 1, of course, because if n was equal to 1, well, it's the same graph. So similar to the other ones, we draw our original graph. But if I have a look at the derivative, if I differentiate it using the chain rule, I'd end up with n function x n minus 1 times the derivative. So that's telling me any stationary points of the original curve will still be stationary points because it's times f dash x. But also notice this, it's times function x. So any x-intercept that we originally had, they will now become stationary points as well. So there's random graph. We're going to do the squared one first of all. So my stationary point here, well, it's a value above 1, so when I square a number above 1, it's going to get bigger. So it's up there. This one here is below -1. I'm talking about magnitude. Obviously, it's above it. Square a number smaller than 1, you get a number that's smaller, but it's going to be positive. So it's now on the other side of the x-axis. I was saying, so all those x-intercepts will now also be stationary points as well. So there's a stationary point, there's a stationary point, there's a stationary point. Now I should have known that anyway, because remember we said when we have polynomials, but it's true for all sorts of graphs, that the root will behave like the power of when you factorise it. So if we're now factorising it to be something squared, all of those roots are now parabolas. The vertical asymptote will remain, because if it didn't exist in the original function, not going to exist in the new function. My horizontal asymptote, well, it's less than 1, so when I square it, it's going to get smaller. Now, again, I'm just talking about magnitude here, but if the original graph was greater than 1, then my new graph will be above my old graph, because the y value will get bigger. And if the original graph is less than 1 in magnitude, then my new graph must be below, because it's going to get smaller. Okay. There's 1. That obviously becomes a key point again. And -1, although it'll be reflected up to +1 because I'm squaring it. Whee! Look at that lovely graph. So let me get rid of there. So we can see that each of those x-intercepts became turning points. The original turning point is still a turning point there at that x-intercept. And so on. It stays positive, of course, because the function is squared.
Can you explain what the horizontal asymptote is down?
Because the original horizontal asymptote was some value smaller than 1.
Yeah, but why does that have to change?
Well, because if you square the horizontal asymptote, then, because what we say out at infinity, it's telling us what's happening out at infinity.
Yeah.
So I know the y values are getting close to this one, but now it's going to get close to that squared. Yep. Okay. So if it's even, which squared was, it's always above the x-axis. If it's odd, the sign's going to stay the same. So those stationary points aren't going to be turning points, they're going to be points of inflection. So like our cubic, because now the power is going to be 3 or 5 or whatever the odd number is. So let's have a look at cubed. Cubed. So turning point goes even higher now, because again, a number bigger than 1, when you cube it, it's going to get bigger. The x-intercepts will stay the same, but they're now going to be stationary points. Oop, horizontal asymptote, again, will become smaller. Vertical asymptote will remain. Cube 1, you get 1. Cube -1, you'll get -1. So, yeah, it's a little bit dodgy there, but I'm trying to get those horizontal points of inflection at the x-intercepts. That's what I was attempting to do with that particular graph. There we go. So there are our power graphs. Let's do a couple of those.